Today's class I'm going to discuss some properties of pi function. If d is a positive divisor of n, then sum of all the values of phi of d is equal to n. It says for an integer n, for a positive integer n, then d is nothing but the positive divisors of n, then the sum of all the values of phi of d is nothing but n only. Okay, this is the first property. This was first noticed by Gauss and it is said as a Gauss theorem. It is called as a Gauss theorem. For each positive integer n greater than or equal to 1, n equal to summation phi of d, the sum being extended over all positive divisors of n. See, I'll just explain you with an example. Suppose I have n equal to 6. Okay. Now, what are the divisors of n? Say d is any divisor of n. They can be 1, 2, 3 and 6 itself. These are the divisors, positive divisors of n. Now, I have to calculate 5 values of these divisors, right? Phi of 1. I hope you know how to calculate. Phi of n is nothing but number of integers less than n which are relatively prime to n. Here n is 1, so phi of 1 is 1. Phi of 2, next divisor is 2, so phi of 2, number of integers less than 2 which are relatively prime with 2, that is only 1 which is 1. Okay. And then phi of 3, 1 and 2. So, there are 2 integers which are less than 3 and relatively prime to 3. Then phi of 6, 1 and 5. So, it is 2. Now, add up all these phi of d values, summation phi of d. Okay, it's 1 plus 1 plus 2 plus 2. So, it is 6 in turn, which is nothing but n only, right? It's easy to understand with, when we take particular examples, but let us prove this now in general. Say n is a positive integer, it is mentioned, it is greater than or equal to 1. So, let me take a divisor of n, say call it as d. Let d divides n and I will consider the set SD. I don't note it as SD, I'm sorry, SD is nothing but set of all those integers. When you take their GCD with n, it gives you the GCD d. Okay, set of all those integers such that it is less than or equal to n and its GCD with n is d. Okay, I am considering SD, set SD is a set of all integers which is less than n, and when you take a GCD with n, it gives you a GCD d. Okay. Now, I can rewrite this set as set of all integers such that 1 less than or equal to m less than or equal to n. Can rewrite this GCD of m by d comma n by d equal to 1. Okay. Now instead of writing m by d every time, I'll just use the notation say k. Now set SD is set of all those integers belongs to Z such a way that 1 less than or equal to k less than or equal to n by d, and in fact everywhere I have to write and, it's okay, and GCD of k comma n by d is equal to 1. Now what is this? This is a set of all those numbers which are less than n by d and is relatively prime to n by d. So this is same as writing phi of n by d. Okay. Now set SD has got is equal to phi of n by d. Now I have to count the number of elements in class SD, right? To do the enumeration of it. See now, observe one thing. GCD of m comma n is d if and only if GCD of m by d comma n by d is equal to 1, right? If they are relatively prime, then only I can write it like this, or the vice versa. Therefore, I can write number of integers in class SD is equal to number of positive integers not exceeding n by d, that are relatively prime to n by d, right? Same statement, just rewriting it, same statement, I am rewriting it, okay. Number of integers in class SD is nothing but number of positive integers not exceeding n by d and they are relatively prime to n by d. So I can just directly write number of integers, so it's nothing but phi of n by d, right? And each of the integers n in say the set 1, 2, 3 up to n, they lies in exactly one SD, one class SD, right? See, I'll explain this with an example again. Each of the integers in n in this lies in exactly one class SD, right? Therefore, how many integers are there? N integers. Therefore, n equal to sum of all phi of n by d, summation runs over all the divisors. Therefore, phi of n by d is same as writing phi of d. So, n equal to summation phi of d. D divides n. See, hence the proof, but I'll explain you again with another example. Suppose I have n equal to 10, okay. So, the integers are 1, 2 up to 10. Now, what are the divisors of 10? D may be 1. Divisors of n which are relatively prime to n, that I have to count, okay. So, 1, 3, 7 and 9. So that I can write phi of n that is phi of 10 in this case is equal to 4. Now I have to take positive divisors of n. Okay, so this is not D. I'm just taking the numbers which are relatively prime to this. So the positive divisors of n, what are they? 1, 2, 5 and 10. These are the positive divisors. In fact, D belongs to this, right? So we'll take up the class SD. SD first, D value I'm taking 1. So S1, it is nothing but number of positive integers not exceeding n by D that are relatively prime to n by D. So class 1 numbers set of integers, okay, which are less than or equal to n, and their GCD is 1 in this case because I'm calculating S1. What are the numbers which are giving you GCD 1 when you take with number 10? So it is 1, 3, 7 and 9, right? In fact, you check with this. It should be equal to phi of n by D, right? So GCD of, or in fact phi of n by D, n is 10 and D is 1. So it is phi of 10. 10 is nothing but 4. So how many integers are there in this? 4 integers. Okay. We'll take up S2, set of numbers which are less than 10 and gives you GCD 2. 2, 4, 6 and 8, right? Now take up number of elements, number of integers not exceeding 10 by 2 that are relatively prime to n by D. So this is 10 by 2, it's 5 and it's 4 again, right? Similarly S3, try to do it by yourself. Sorry, not S3, it is 5. S5 should get the GCD 5, that is only one possibility. And now phi of 10 by 5, that is phi of 2, which is equal to 1. Similarly S10, it's only one number 10 and phi of 10 by 10 is 1, right? So now sum up all this, summation phi of D. Phi of n by D is same as taking phi of D in the other way, not exactly the same way, in some other order. So summation phi of D, D should divide the number n, that is 10. Okay, so which is nothing but phi of 10 plus phi of 5 plus phi of 2 plus phi of 1. So which is nothing but 4 plus 4 plus 1 plus 1, which is equal to 10, which is nothing but n only, right? See, this is phi of n by D. See, if you take this, this is phi of 10, this is phi of 5, phi of 2, phi of 1. Okay, that's 1, 2, 5, the other way around. So phi of n by D is same as phi of D in some other order. The same thing I am explaining over here. Okay, that's why we are writing phi of n by D is nothing but phi of D, so that their summation is nothing but the integer n only. Okay, let us look at another property. property says for n greater than 1, the sum of all positive integers less than n and relatively prime to n is nothing but half into n into phi of n. It's very useful property of phi of function. Let us prove it first, then we'll go for the example. Say let a1, a2, a phi of n are the positive integers less than n and relatively prime to n. Okay, less than n and relatively prime to n. Now see, we know GCD of this AI comma n is equal to 1, relatively prime to n, right? These AIs are relatively prime to n and they are less than n. Okay, so this I must be between 1, greater than or equal to 1, and it should be less than or equal to phi of n. Okay, this we know. And this is also can be written as GCD of n minus ai comma n equal to 1. I hope you know this. We studied in our earlier classes of GCD. See, I'll just explain you. Suppose you have GCD of a comma n equal to 1. Then there exists some, say, p and q in such a way that you can write ap plus nq equal to 1. Okay. What I do is I'll just add and subtract aq to this statement. So that I'll get ap plus aq plus nq minus aq equal to 1. Now I can take up a outside, so that a into p plus q. Here I'm just taking plus n minus a into q, right? It is equal to 1. Now this is some integer and this is some integer, therefore I can just write GCD of n minus a comma a is equal to 1. Same thing I'm doing over here. So GCD of ai comma n equal to 1. It is same as writing GCD of n minus ai comma n equal to 1. So when that is the case, this n minus a1, n minus a2, like that, n minus a phi of n are nothing but a1, a2, a3, a phi of n in some other order, right? So I'll just mention it. This just implies n minus a1, n minus a2 dash dash n minus a phi of n are equal to a1, a2, a phi of n in some order, right? So that what I can do is I'm just adding all a1 plus a2 up to a phi of n equal to n minus a1 plus n minus a2 dash dash n minus a phi of n. So the right hand side will be, how many times I'm taking n? Phi of n times, right? So n into phi of n, or sorry, phi of n into n minus of this a1, a2, a phi of n, a1, a2, a phi of n. So I'm taking this to left hand side now. It's already a1 plus a2, it is there. So twice of that, a1 plus a2 dash dash a phi of n is equal to n into phi of n. So I'm taking 2 down over here, so a1, a2 dash dash a phi of n is nothing but half into n into phi of n. What are this? This is nothing but sum of all the positive integers of n, which is relatively prime to n. The sum is nothing but half into n into phi of n. Okay. So this I am taking because say I want to find all the sum of all the positive integers less than n and which are relatively prime to n. So I am taking that since it is given that they are equal to n minus a1, n minus a2, n minus a phi of n in some order. Therefore I am replacing this a1 with n minus a1, a2 with n minus a2, like that I am doing. And I am just rearranging the terms and I am getting the formula for sum of all positive integers less than n and relatively prime to n. It is equal to half into n into phi of n. Okay, I will just explain you with the small example. Say n equal to 30. What are the integers, positive integers less than n and which are relatively prime to n? Take up the numbers 1, 7, 11, 13, 17, 19, 20, 29, 23 and 29. Yeah. Now take up AIs. AI, if you take sum of all these AIs, if you want sum of all these AIs, you are going to get 120. Now I want to prove this is equal to half into n into phi of n, right? What is phi of n? It is 8. Yeah, it is 8. So you can check this is same as writing now half into 30 into 8, right? 2 4s and 4 into 30 is 120, so it's fine. See now AIs, see if you take AI as 1, just to explain this, these AIs are nothing but n minus AIs in some order. For that sake, I am just explaining. If you take AI equal to 1, then what is n minus AI? 30 minus 1, it is 29, right? Next, if you take AI as 7, then n minus AI will be 23. If you take AI as 11, then it is 19. Okay, like that you can check. So you will get these numbers in some other order, I mean in reverse order when you take n minus AI. Okay, so this is the second property of Euler's phi function.